Hey everybody, Dr. Phil here. So this is going to be a probably a fairly brief video on sampling methods, and what is known in statistics as the central limit theorem. So let's start talking about research and sampling. So research in the context of sampling. So research, what is research? So we can define that as the process of studying a problem, question, or hypotheses. Data are collected on relevant variables by sampling from a clearly defined population. Then statistical, or I should say, and or analytical techniques are applied to summarize and analyze the data. The results are the basis for making inferences and stating conclusions about the population. The primary goal of sampling is that the sample is unbiased, right? So when I say unbiased, it's completely randomized. There's no favoritism in like every person or data point in the sample has an equally likelihood, equal probability, if you will, of being picked out. So the primary goal of sampling is that it should be representative of the population. Otherwise, the sample isn't really going to help you, right? And it should help you to draw valid inferences and conclusions about the research. So we need to determine if conclusions are biased. So what is the purpose of the research study? What is the population? And we need to understand how a sample was selected from the population. Ergo, was it done so randomly? Was there any kind of bias introduced, perhaps unintentionally? Inferences and conclusions from a sample should be limited to the population the sample came from. So what they mean there is that if you draw a conclusion about, say, a certain type of a bird, then it's only about the conclusion is it's about this type of bird. You couldn't necessarily extend that or extrapolate that to all bird species. Convenient samples are easy, but often yield biased samples and conclusions. So you got to be very careful about the size, like the size of the sample as one thing. And like I said before, you've got to be very careful about making sure that the sample is randomized. The reasons to sample from the population are primarily related to the time and cost needed to collect the data. So number one, to contact the whole populations would most likely be time consuming. If you were like, we're going to do a study on males in the US from ages, say, 30 to 49. Think about it. I mean, that would be millions and millions of people, right? There's no way you could ever do that. The cost of studying all the items in a population could be prohibitive. Imagine sending out a survey to all those people I just said. It'd be so expensive, it'd be ridiculous. Number three, the physical impossibility of checking all items in the population. And number four, the destructive nature of some tests. And we'll talk about a couple more of those things here in a few minutes. So, different types of sampling methods. We have what we call a simple random sample, where all members of the population have the same chance of being selected for the sample. That's a good thing. A systematic sample. A random starting point is selected, and then so they're gonna say like every kth item. So like it could be every third item, every 10th item. They just put K in there because that's gonna depend on what you're doing, right? So you start at a random point, and then from then on, it's like every 5, every 10. The stratified sample. The population is divided into several groups. We call those strata, and then a random sample is selected from each stratum. So an example of a strata could be income. So maybe everybody that falls in this tax bracket is this strata. If you fall in the 20% bracket, you're this strata. If you fall in the 30% bracket, you're this extra, well, higher up strata, so on and so forth. And then we have clustered sampling. The population is divided into primary units. Then samples are drawn from those primary units. Then I wouldn't say the last one, but another one that we should talk about very briefly is the simple random sample. So a sample selected so that each item or person in a population has the same chance of being selected. So if we go back just real quick, simple random sample, right? So pretty much the same thing. This is widely used. Uses a table of random numbers, often to kind of help you generate the randomization you need. You can also use statistical software to generate random numbers. There's also a function equals rand, R-A-N-D in Excel. You could also use that too if you wanted. So with a systematic random sample, a random starting point is selected. And then as we said, every kth member of the population is selected. So that could be every 5th, every 10th, every 20th, every 28th, so on and so forth. Now, the thing about simple random sampling is it may not always be practical. You don't have a list of the entire population, so it makes a whole like kth member of the population thing kind of difficult to do. By way of example, let's say that Stude's grocery store wants to study the length of time customers spend in their store. So they randomly select the days of the week, the times, and the starting point of the study, and then they systematically then select the customers and measure the time each spends in the store. All right, so let's talk a little bit about a stratified random sample. So a population is divided into subgroups called strata, as we said before, and a sample is randomly selected from each stratum. So strata can be formed based on members' shared attributes or characteristics. So the example I was just giving you could be people, could be earnings, so it could be people in different tax brackets. Those would represent the strata. It guarantees that each group is represented in the sample because there are going to be people. There are going to be people from every one of those tax brackets. So their example is advertising expenditures, right? So you can see the five stratums here, and then you can see the profitability, return on equity, and then you can see company five is obviously unprofitable, and then as you go up to number one, it becomes more profitable. And then you can see the number of firms that fall into these categories. So, for example, five firms are apparently running a loss at present. The frequency, like the 0.001 relative to 1, you can think about the number of firms just back into that total. And then you can see over here they've got the number sampled. So like 1, 5, 27, 16, 1, and 50. So that's 50, of course, is the total. All right, cluster sampling. So this is more of a geographical kind of technique. Population is divided into clusters using naturally occurring geographic or other boundaries. So, for example, counties could be, so like Forsyth County, Guilford County, Davidson County, Surrey County, so on and so forth. Then clusters are randomly selected and a sample is collected randomly from each cluster. So often employed to reduce costs. This is often a cheaper way to get the sample that you need. Their example, sampling residents in the greater Chicago area. So you can see you got Lake Michigan, you got Kenosha, Lake, you got Cook, DuPage. Of course, these are all the counties that are around the greater Chicago area. All right, so let's talk a little bit about the sample mean as a random variable. So sampling gives a random selection of objects or individuals. The data are used to compute sample statistics. For example, a mean could also be a median, a mode, so on and so forth. Each sample is different, so each sample mean will of course be different. Sample statistics, such as the sample mean and the standard deviation, are random variables with probability distributions. Okay, those we'll talk about those a little more in a second. And then finally, sampling error is the difference between a sample statistic and its corresponding population parameter. All right, so sampling distribution of the sample mean. So a probability distribution of all possible sample means of a given sample size, which really, if you think about it, possible sample means is really almost going to infinity as sample sizes get larger and larger. The distribution of all possible sample means, computed from all possible samples, is normally distributed. Later, we can make probability statements about the size of a specified sample error. So that those 2 points will make a little more sense here in a second. So, example, the distribution of hourly earnings for employees. So you can see we've got, let's see, 1, 2, 3, 4. We got 7 employees here, and then we've got how much each employee earns, right? So like Joe earns 14, Bob earns 16, so on and so forth. And you can see the samples we've got here. So the first sample is Joe and Sam. They both make 14. So if you add those together, 28, divide it by 2, because the mean is an average, right? And then if we just pick one more, let's say sample 7, Sam and Sue, we go up to the chart. Sam makes 14, Sue makes 16. You can see the 14 and 16 here. If you add those together, again, 30 divided by the mean, which of course, well, divided by 2, excuse me, gives us that mean of 15. So this is just, you think about how many times that they can kind of do this and come up with different combinations, different permutations, if you will. So, and then what they've calculated is a probability for each of the means. So we got the sample. If the sample mean is 14, and then 15, and then 16 and 17. If I just go back here really quick, and remember the mean is the average because you might be looking at the 17 and saying, okay, I don't see a 17, but remember that is the average, right? And then they're saying, okay, so like 3, 9, 6, and 3, all of these in the 21. And then we're calculating our probabilities. So like 3 into the 21 is going to give you that 0.14. 9 into the 21 is going to give you that, just call it 43%, right? 0.4285. And 6 over 21 is going to give you that 0.2857. Down here, they're just showing you the population distribution, and then the sampling distribution of the sample mean. So you can see that 16 well, 14 and 16 were both very popular, and then 18 was way less popular. If we go back real quick, you can see here there was Ted that was making 18, and that looks like that was the only person. Okay, the next thing I want to talk about is what we call the central limit theorem. So it's something that sounds very fancy, but it actually describes something very simple. So if samples of a particular size are selected from any population, the sampling distribution of the sample mean is approximately a normal distribution. The approximation improves with larger samples. What they're saying there in a nutshell is the bigger your sample size, the more of a normal distribution it will look like. Determine the distribution of the sample mean without any information about the shape of the population. So if it's symmetrical, the normal shape of the distribution of the sample mean with samples, as you may see it with samples as small as 10, skewed or has thick tails, may require samples of 30 or more in order to observe the normality feature. So it's like the bigger the sample, especially if you've got samples where they've got numbers all over the place, you just need more of those data points within that sample to make it look like a normal. Think about the bell curve, like the normal distribution. So by way of example, so you can see like the populations are up here, right? And you can see n equals 2. It kind of looks like a normal distribution. If we increase it threefold to n equals 6, you can see it's now looking a little bit normal. And then once we hit n equals 30, you notice how everything is more clustered around the mean. So, example years of service for employees. So 40. So they've got all this data here, right? And you can see they've got the frequency, they've got the years of service. So you kind of look at that and you say, okay, it looks like it's kind of skewed right to the right hand side. It maybe looks on the left like a bit of a normal distribution, but you certainly see a lot of skewness there. So what if we have a sample size of 5? So if you look if you look over here, you can see if I go back, it's looking a little more like a normal distribution now, but it's still, you still gotta, it's getting there, right? But it isn't there. Let's just say like that. If we increase the sample size to 20, you notice how it's gone from that to that, and now it's getting more and more clustered around that mean. That's this idea of the central limit theorem. And as you can see, if we kind of bring these all together, you can kind of see this is how it started looking at the beginning. It was kind of like, yeah, it kind of looks like a normal distribution, but more on the left-hand side. But then that doesn't really account for the years of service, 9, 12, 15, and 18. But you notice as we start to add more in, if we increase the sample, if you will, you see how in the top box on the right, you can see how it begins to look more like an normal distribution. And then if you look at the one below, now we added, this one was 5, this one was 20. So again, the idea here is pretty simple. The bigger the sample size, the more like a normal distribution it's going to look. So the mean of the distribution of sample means will be exactly equal to the population mean. If you think about it, it makes sense because if you've taken this like kind of like infinite number of samples, they all ultimately represent the population, right? They're just different pieces of the population that you're pulling out for your sample. So it makes sense that the population mean should equal the mean of the population. The mean of the population should equal the mean of the sample. The standard deviation of the sampling distribution of the sample mean is also called the standard error of the mean, and it's typically expressed as you see here. So we have sigma. This is known as most of us call this x bar equals and then sigma over the square root of n, which is the sample size. So that's a nice bit of math for you. What do I really want you to know? As the sample size increases, the dispersion decreases. So that kind of, you notice how like the more we added into the sample, the more it was doing this. It was becoming more clustered around the mean, as it says, right? Ties us nextly into the next point. Distribution narrows around the mean. And then the shape becomes more normal. Now, when we say normal, I know that sounds weird, but like we're talking about the normal distribution, right? We're talking about that bell curve. So that's pretty much the idea of the central limit theorem. Okay, as always, thanks for watching, and I will see you in another video.